Hey there, folks. Good morning. In today's problem, we're provided a rod of uniform density, which has a mass and length that's given above. This rod will rotate in a horizontal plane about an axis through its center, which I've indicated using that black dot there in the middle. To make things easier to see, this picture is drawn from a bird's eye perspective. So we're looking down onto that horizontal plane here. Before the rod begins to rotate, we're going to stick some rings of equal mass on each end. These rings remain at the same distance from the center of the rod as we spin it up to an initial angular speed of 30 revolutions per minute. And once the rod reaches that rotational value, we allow the rings to move freely, and eventually the rotation will cause them to fly off altogether. Now, with that said, there's two things that the problem wants us to do here. In part A, we need to solve for the angular speed of the entire system once the rings have moved to the ends of the rod. Then in part B, we'll solve for the angular speed of just the rod after the rings are no longer in contact. To start, let's label the beginning location of the rings as x initial and the starting angular speed as omega initial. Then, once the rings are at the end of the rod, the new ring distance will be x final and the new angular speed will be omega final. To solve this problem, we have to use a quantity that we haven't seen before, and that is angular momentum. There's a couple ways to define angular momentum, as we'll see in the future, but this definition is all that we need for now. And like linear momentum, it's conserved under a special condition. If there's no external net torque exerted on our system, the initial angular momentum will be equal to the final. Let's go back to our picture and see if that applies. Since all of the movement of this system occurs in a horizontal plane, we can ignore the force of gravity. There are, however, contact forces between the objects, and those forces act at a distance from a point of rotation, which means the rod and the rings are exerting torques on one another. But these are what's known as internal torques. It's a torque from one object acting on another object from within the same system. Those kinds of torques are special because they allow objects to transfer angular momentum among each other without changing the total amount. And since there's no external net torque occurring here, the angular momentum is conserved, and we can take advantage of that to solve our problem. I'll start by switching out L initial and L final with the I omega definition that we saw from earlier. And we can isolate omega final by dividing both sides by I final. For the moment of inertia expressions, the problem description didn't give us any information about the diameter or the radius of the rings, so our only option is to treat them like particles. Thus, our bottom equation will take on the following form. The moment of inertia through the center of the rod is 1/12 ml squared, and the moment of inertia for a particle is mr squared, which we're going to multiply by 2 to account for both rings, and we'll substitute in x initial or x final for r. Now with everything ready, we can plug in our numbers and report the final angular speed using the same units as the initial. There's no need to convert it to radians per second here. On my calculator, I get exactly 7.5 revolutions per minute. And that's our answer to part A. For part B, the problem description almost implies that the angular speed of the rod changes after the rings fly off. But is that really the case? Let's take a closer look. Remember that the angular speed of an object changes when a torque is exerted on it. If the rings fly off, then there's no internal torques anymore, and there's still no external net torque acting on the system either. So, since there's no torques, there's nothing to even cause a change in the angular speed of the rod. So, it would remain the same as the answer that we found back in part A. And that's it for both parts. And our problem is done. I hope this helps. Thanks for watching, everybody.